Okay, so now we are going to talk about this is slightly, different topic in the sense that how groups are used in kind of uh, in science or other domains and things like that, and how the even the group's understanding of group develop over the years in some sense. So one of the major place where you see groups and how the groups arise in real life or in sciences or otherwise is via symmetry. And you can take also this topic as kind of a new topic as an application of groups, or you can also think of it as how groups arise, or you will see this in your other courses where people will be talking about symmetry or how groups act or how groups arise, and often these are very confusing if you are not seeing this yourself uh, in this sense. So let me try to do this, and let's try to understand all these topics a little bit. Not in a great detail, but I will give you some references which you, if you're interested, you can read about this. Okay. So what is a symmetry, right? I mean, in the sense of real world. So today I have some slides. I had written earlier some slides to give some talk somewhere else. So I will use those slides essentially, kind of extended version of that slide. So over next 2-3 lectures, we'll cover this topic and hopefully we'll see things in more detail. And we'll try to also conclude some of the things. Yeah, so I hope this is okay with you all. And you can ask me questions and whenever you want. So this is also kind of this will answer also your question as motivation. What are the motivation? This is one of the situation which you can take as a motivation. So what is a symmetry? I mean, what do you think of symmetry? What symmetry could mean in some sense, or layman language? What do you call? Do you want to answer?
Any action which will leave the system unchanged.
Well, yeah, you are giving scientific definition, but I said that what symmetry means to a layman. You know, if you did not know as much of science as you know, yeah. So Earth says that it's something to do with pattern, yeah, or something with what you associate with beauty. When you see some artistic object, some pictures or some monuments or something like that, you say that, oh, this is beautiful and it's so symmetric in the sense. So often you mean symmetry by, like, it has some kind of regular pattern. It is something which repeats itself. It is that is what you would say is something is more symmetric, right? Um, for example, when you see a fly, or when you see something, right, or a butterfly, when you see that, okay, it is duplicated, that's what you, one half is the same as the other half. Yeah, I mean, we have two hands, which is what is a symmetry in some sense, because they are supposed to be a duplicate of each other in a way. Uh, Athar says that if you look from different sides, object looks same. Yes, so that is what it is. In a hi-fi language, you call it chirality. Yeah, that is a physics language. We'll
And
come to
as
that.
kids, we were taught lines of symmetry, and yeah, that is like the earliest memory, I would say.
Sorry, what?
As kids, we were taught lines of symmetry in geometry, right?
Yes, yes, yes. So
That
in
is like,
geometry also you see this term being used, symmetry. And yeah, so we have a kind of a basic idea of what symmetry means, right? What we are trying to do here is that we'll try to uh, think of how to measure symmetry, yeah, and then we'll see how group theory enters there. So groups are supposed to be symmetries of some artistic object in a way. I mean, that's what the layman language would be. Uh, Groups are fundamental to engineering, uh, uh, as we know. So obviously, how it appears there, you have to understand that groups are tool to explore things in science, and a good understanding of group theory will be very, very useful and helpful if you deal with those objects. Um, Obviously, we know the definition of group and group action, which we will use freely here whenever they require. So we are not going to spend time recalling that. So let me begin with some very, very basic and trivial, things which you might have seen in schools even. There's a question. Have you seen tiling of a plane? I mean, we all have tiles in our houses, or in institute building, or even on pavement of the road and things like that. Uh, uh, what kind of tiling you have seen? You must have seen tiling by, like, triangles. You might have seen tiling by squares, and you might have seen tiling by hexagons. The question is that, have you seen tiling by pentagons?
No.
So, or any other higher, like,
I
octagons or
think
something like.
I don't remember properly, but tiling with hexagons plus pentagons is there, if I'm not wrong.
Yes, yeah. So, the question is that, what do I mean by tiling then, right? Uh, because the tiling is a complicated thing. So, what I'm talking about tiling here is a very basic, simplest possible tiling, where you are given, so what is called regular tiling. So you are given uh, 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 n gun for a fixed n, and you are given unlimited supply of that, and you are trying to put them together to fill the whole plane, without, overlapping, without even like, kind of cutting across or something like that. So that's what I mean here by tiling. uh, so if we go with this definition, which is a very basic kind of tiling, then it is only possible to do with 3, 4, and 6. Yeah. And of course, you're not seeing, for example, pentagon tiling. And the question is that, can we prove such thing mathematically? If you go slightly, if you want to think of a slightly advanced version of tiling, where you might be given a combination of two different tiles, uh, then also you can classify, you can try to classify, and there are more complicated version of that. But here right now, I'm just talking about a very basic, trivial situation of tiling, which is what is commonly seen in our houses and things like that, right? So, for example, triangular tiling will look like this. I mean, you have an equilateral triangle, and you are going to fill the whole plane with equilateral triangle. Something like this will be a square tiling. You have squares, and you can fit them together. You cannot cross over or things like that. Again, the tiling depend on shape of the plane. I'm asking to fill the whole plane R2, infinite plane. I mean, that is my definition right now for mathematics sake. I'm not trying to tile, like, because often the tiling, I mean, the real life tiling is, of course, you are trying to fill the floor of your house, which is not infinite, obviously. But for mathematics sake, let's say that we are trying to fill the whole R2. That is what is my definition here. Is it necessary to have equilateral triangle? Right now, I have taken that as a definition, that I'm trying to fill the plane with a regular n-gun, basically, which has all the sides same. So I will either take the equilateral triangle or square and things like that. Of course, you can ask more general version of this question, that if you are given kind of not necessarily equilateral triangle, whether it is possible to do things and all that, right? So uh, uh, you can have more complicated definition of tiling, and then you can try to answer question there. But as you know, when you have more complicated definition, it becomes a little more complicated also to answer mathematically, right? So let's try to understand mathematics behind it in a very easy situation, and then if you're interested, you can read more about it. Okay, and this is how hexagon tile will look like. Yeah. So again, what is the meaning of tiling the plane? I have whole plane R2 which I'm trying to fill. It's an infinite plane, right? X-axis, Y-axis, and it's an infinite plane which we are trying to fill with, given like, unlimited supply of uh, n gun, n is fixed. So obviously you can see that this question then makes sense for n equal to 1 or 2. So obviously n is greater than equal to 3, right? So we can do a very easy high school level computation and prove that this is what the result is, that you can only do with n equal to 3 4, and 6. And here is a quick proof. So we fill the plane with tiles which are n-gun, as I explained. What does that mean? And let's say at this particular corner. So when you are trying to put the tiles together, uh, I will look at this particular corner where tiles meet. Right? I'm not allowed to. I'm not allowed to kind of put a tile like this. Right? This is not allowed. Right? And I'm also not allowed that tile overlap. I mean, this is not what tiling means, right? So I look at a corner. I will look at this corner where these tiles meet, and suppose m of them meet. So I have 1, 2, 3, and so on. I'll call it m, and we will try to determine the value of m. Yeah, and these tiles are supposed to be n gun. So I have two numbers. N is given to me, and m of them meet at the corner. Is that clear? So now with this, a simple high school calculation will tell you that if I look at this internal angle, right, because I have to put them in a plane, the sum of this internal angle should be 2 pi. But I'm taking regular, each one of them are same, right? So I can just multiply n times internal angle of one of them, and that should be equal to 2 pi. So this is one of the condition of tiling. And we'll solve this equation and see that this equation is just enough to the solve our problem. So let's try to look at this equation. Now I need to know what is internal angle of n gun. Do you know what is internal angle of n gun? Anyone remembers formula? So this is the formula. I'll tell you what the formula is, and it's not very difficult to also kind of prove the formula. So internal angle of an n gun is n minus 2 pi by n. Okay, and a very easy way to kind of understand this formula is that suppose I have this n gun given, right? I have this. So what I do, I fix a corner and I start making triangles, right? Now, how many triangles I can make? Suppose this was n gun, right? So if I had a square, I can make 2 triangles. If I had a pentagon, then I can make 1, 2, 3, right? So that means it is n minus 2 such triangles, right? And the sum of the angles of one triangle is pi. So I will take n minus 2 pi. But n minus 2 pi will give you sum of all possible internal angle of this n gun. So I have counted all of this. So I divide by n to get one of the angles. So this is n minus 2 pi by n. A quick proof of this. You don't need to remember the formula. You can very quickly visualize this internal angle of an n gun. So now substitute this value into this equation here, and the equation becomes m times n minus 2 pi by n equal to 2 pi. I can cancel out this pi and rearrange the formula by dividing by m into n, and I get this equation: 1 by n plus 1 by m equal to half. This is the equation I get. Is this clear? This is just rewriting this equation. So of course I cancel pi and pi, and this becomes m times n minus 2 equal to 2n, and then divide by mn, and then I will get 1 by n plus 1 by m equal to half. I move this one this other side. So good. This is what the equation I get. And where n and m are both integer, because n is supposed to represent the number of sides of your n gun, so it's an integer. M is supposed to be also the number of tiles meeting at a corner, right? So these are all positive integers. And my claim is that both of them are greater than equal to 3. So n is certainly greater than equal to 3. There is no tiling by 1 gun or 2 gun. So you need at least 3 gun, which is equilateral triangle. So n is certainly greater than equal to 3. And if I take 2 of these objects, they're not going to fill the plane, right? So I need at least 3 at a corner. So you can see this, that this is also a condition that m is also greater than or equal to 3. I'm just trying to simplify to solve this equation, right? So if I take m and n greater than or equal to 3, you can check that either n or m, this is not possible if n and m, either one of them are greater than or equal to 7. Because if one of them is greater than or equal to 7, then 1 by n plus 1 by m is going to be less than or equal to 1 by 7 plus 1 by 3. 3 will come from here anyway, right? Which will be, you can quickly compute by calculator and see that it is 0.47, which is strictly less than half. So either n or m, none of them can be greater than or equal to 7, basically. So you restrict the value of m and n between 3 and 6. Is that clear? Very quick calculation, simple calculation will give you this. So I have now equation 1 by n plus 1 by m is greater than is equal to half, and n and m are both are greater than or equal to 3 and less than or equal to 6. And you can try to substitute. I mean, now there are only like few choices. You can try to substitute the values and see when you get half. And it will turn out that there are only these 3 possibilities where you get the value half. It's high school level mathematics. I mean, you can easily calculate this yourself and see this answer. Yeah, and these 3 cases are exactly the one which we know that it happens. So 3, 6 corresponds to triangle, tiling by triangle. And let's go back to the picture and see that this is what it is. So if I look at this picture, this is tiling by triangle. And if I look at a corner, how many triangles meet at this corner? We can count that 1, 2, 3, 4, 5, and 6. Yeah, it's clear here. Okay, good. And the second answer was 4 and 4. So the tiling by square, and you can see that the 4 squares meet at a corner. And then the third one was 6, 3. So the tiling by hexagon, and 3 of them meet at a corner. And these are the only possible solution of that equation. And all of them give actually a tiling.
So the triangle tiling can be reduced to hexagonal tiling.
Triangle tiling can be reduced to hexagon tiling. What do you mean by that?
If we take 6 of those triangles together every time, we get a hexagon, right?
Yeah.
I mean,
so all you were trying to say that the answer to the solution is symmetric.
Okay.
Yeah.
Yeah.
And that you also see the equation we get 1 by n
6
plus
and
1
3
by m
and 3,
equal to half.
6. Yeah.
Yeah, that is also symmetric, and the solutions are also symmetric. Right?
Yes.
That's what it means roughly. How do we prove that m is greater than or equal to 3? I mean, if you take any n gun, if you take 2 of this, these are not going to be enough to fill a tile, fill a plane, right? Even if you take 2 triangles, you need more than that to kind of fill a plane. I mean, any object, just 2 of them are not going to fill. You have to, you can just, verify this by calculation. Again, you can do it by multiplying the angle by of one of them by 2 and see if that gives you pi. It won't, right? So that is another way of saying that this condition is a mutual condition.
Just from looking at the equation, if one of them is half, then the equation will never be satisfied. If one of them, if n or m is less than 3, then
then
it
also
will by default be greater than half.
Right. It will be always greater than half. So that is also another way to say that. If n or m, any one of them is 2 or less than 2, 1 or 2, you'll see that this equation will fall in trouble. Okay, so that's another proof mathematically. Okay, good. So now we have done a very quick revision of our high school level maths to figure out that there are 3 possible tiling of plane. Very basic kind of tiling. I'm not looking at very generalized version of tiling. There are more complicated version of tiling. If you are interested, you can try to read it. You can even look at the Wikipedia article on this, which will give you a lot of references, and even higher version of more complicated version of tiling and what is known mathematically and what is not known. There are several open problems in this direction. Okay, but what we want to understand group theory, right? So what is symmetry here? So symmetry, as somebody was trying to point out earlier, is a motion of the plane. What kind of motion? An isometry of the plane which leaves this object invariant, right? So let's say if I apply some kind of movement, some kind of motion, and if it leaves this particular object to itself, then that is what is the symmetry. Can we quantify this mathematically, right? So for example, let's say here, when I have a tiling of the plane, I can translate it by certain amount, and I see that the whole tiling goes to itself, right? So for example, let's look at this is a square tiling. Let's say the side of this square tiling is unit amount. Okay, so let's suppose look at this. If I shift the whole tile by this amount, right, on the right side, you see that nothing changes. If I shift vertically by this amount, also I see that the whole thing doesn't change. Think of it as an infinite picture. I mean, not a finite picture. We are trying to tile the whole plane. Our whole plane R2 is tiled. So if I shift by unit amount this side, or if I shift vertically by unit amount, the tile goes to itself, right? So these are kind of symmetry. This is one of the symmetry you see here, the symmetry by translation. The question is that are there more? So you will can you tell me if there are more symmetries or these are all?
We have rotation, right?
We can also rotate. For example, if you are looking at the square tiling, if I rotate around 1 point by what, pi by 2, then still the whole thing goes to itself, right? So there are other symmetries also, and these symmetries come from the symmetries of the n gun, delta n in that. So let's call n gun to be delta n just for the notation sake here. So if n is 3, then delta n is equilateral triangle. If n is 4, then delta n is supposed to be a square, and things like that, right? So just a notation. So if I take a symmetry of delta n, that will also give a symmetry of the plane, this tiling of the plane, right? So we need to now understand what are the symmetries of delta n. And if you remember the first lecture, we tried to define symmetries of delta n, and we said that it is something like dihedral group or something like that. So now is the point to clearly tell you why this that was equal to I mean, it has 2n elements and things like that. Now we'll prove that. So let's do that. So what measures symmetry? This is the question we are trying to answer, and we are going to measure the symmetry by looking at this kind of motions of the plane which leave the object invariant. And eventually the theorem will prove is that this forms a group. You know, it's a subgroup of some big group, and we'll try to compute this subgroup. That is what is the main problem. So given an n gun, let's say it is delta n, and we want to associate symmetry group to this. Okay, more symmetries, the more symmetric an object is. That's what we will say. For example, if I look at a triangle, so okay, I have some objects. Let's look at a triangle here, right? You can see this, right? So this triangle has, like, you know, I can rotate it around its center, so that just if I look at this triangle in a plane, then it has no translation symmetry, because this is just one single object. If I translate it, it's not going over itself, so there is no translation involved here. I can only rotate it by 2 pi by 3, and the twice of that, and then if I do one more time, then I get back to itself, which is the identity. And I can also reflect, so I can do this reflection along the vertical line, and same thing about the line passing through this corner and this midpoint, like this, right? So there are 3 of this. So there are in sense 6 symmetries, and this is what we had called dihedral group. So this is with the 6th element, and if you take a slightly bigger object, let's say something like a square, and you will get here 8 element, right? So one can say roughly the larger number of symmetry this has, we'll call it is more symmetric an object, right? I mean, we call something which has more sides is more symmetric, and which has less side may be less symmetric. So we can say that the number of these possible motions which leave the object itself is the measure of symmetry. And we'll try to compute that and see what does that mean. For example, here I have drawn a picture of pentagon, and for pentagon, you can see that you can rotate around the center, right? So you cannot translate it. First of all, there is no translation because I have only single object. Let's say it is sitting at this point as a center. So it has no translation involved. But I can rotate it by 2 by 5 and its multiple. That will give me 5 symmetries, including identity. And it has 5 reflections. So reflections by, for example, you can look at the reflections around this line which passes through the one of the vertex and midpoint of the opposite edge. And this will give you 5 of them. So roughly speaking, this tells me that there are 10 symmetries for this particular object. And in fact, if you remember the definition, this is what is the dihedral group. This is what we had told. This is what is dihedral group, right? Is this clear? But the question now you can ask that why there are only 10, only these 10 for this, right? Why can't we have more? So we have to make these definitions precise and compute that these are the only possible symmetries. This is what is the aim of this lecture and maybe over next couple of lectures. This is what we will do. So as we said that what is more symmetric, it is defined, it is decided by the group which is going to come out of this your object. And what are the types of symmetries? So far we have seen this type of symmetries like translation, reflection, and rotation, or it could be complicated combination of that, right? I mean, which we can think group theoretically that will try to find basic motions which keeps you those objects invariant, and their combination. So in group theory sense, it is supposed to be the generators, and other elements are supposed to be the composition of a product of those generators, those elements, right? This is how you understand group theory. For example, I can rotate and they reflect, right? So group theoretically, I'm just trying to multiply the 2 elements. Is this clear? That's how group theory is interpreted here in symmetry and other ways. Okay, so this is what we want to show, that symmetries of delta n is the dihedral group, and it has 2n elements. And we want to prove that it has 2n elements. We know there are 2n elements, and we want to show that there is no more, right? Because I know that there is a rotation by 2 pi by n and its multiple, so that gives me n element, and there are n reflections. So there are total 2n elements. I already know that there are 2n elements which are symmetry of delta n, but the question is to prove that there are no more. So let's do that. Let's mathematically kind of try to write it down. Some terms may not be very well defined right now, but I will do that over next couple of lectures. So right now I'm just telling you in advance that what is the aim of doing all this stuff. So this particular example, we want to complete it so that you can see the point of defining things in more general way. So what is symmetry of delta n? Symmetry of delta n is going to be certain isometries of R2 which keeps the delta n to itself, right? Delta n is the n gun, and we want to claim that this is the dihedral group D2n, and the dihedral group was defined like this with the 2n elements. This is what we want to prove. This is a question mark. So we know there are 2n elements, but why there are no more elements, right? This is what we want to prove. So it turns out that the isometry of R2 is supposed to have translations and rotations and reflections. This we will prove maybe in the next lecture. So orthogonal group O2 comes in picture here. What is O2? O2 is supposed to be union of SO2 and product of this matrix with this matrix. So this is supposed to be a 2 by 2 matrix group which satisfies certain conditions, and it will turn out that O2 has exactly these elements what I have written here. I hope that is clear. I mean, we will make it more precise in the later lecture. Right now, I'm just giving you the definition. I'm literally giving you the elements of O2. In fact, we'll define more generally what ON means. So, so to compute this, I have to find all those elements from here which leave delta n invariant. We did this last semester. Okay, fine. That is very good. So you understand already what it means. But I think not everybody took that course on advanced linear algebra. So anyway, let me repeat some of it. So the orthogonal group O2 is at work here, and O2 is union of SO2 and a fixed reflection multiplied with every element of SO2. So O2 has two cosets. You can see there are two left cosets. One left coset is by identity by SO2. SO2 is a subgroup of O2, and other coset is given by this element. Okay, so every element of O2 is either an element in SO2 or an element this, where SO2 is concretely given. This is the matrix of rotation, right? If I take cos theta minus sin theta cos theta, if I take a vector and multiply this vector, let's say it is x1 x2, and multiply to this matrix here, then whatever you get, it will give you the vector which is obtained by rotation by theta degree. This is the new vector. This is what is the meaning of this matrix. That is why such matrices are called rotation matrix. Okay, so now the question is, what is the symmetry of, okay, this is an interesting question for you to think, that what would be the symmetry of circle? I've been talking about symmetry of n-gun, right? We are trying to compare symmetry of n-gun, and we see that it is finite. It has 2n elements. I have not proved it. I'll prove it in the next slide. But a question you can ask, what is symmetry of the circle? Anyone has any idea? Okay, somebody give answer.
SO2?
Amol gives answer O2.
O2, okay.
Why O2? Why not SO2? Why not more?
I mean, at least it is O2, right? Because you can rotate and reflect it by any angle, and it will remain invariant.
Yeah, exactly, that's correct. So we'll prove this also, that it is actually O2. In this sense of isometry, what I will define here, right? And this is also in some sense clear, because if you take higher and higher size or n-gun and tending to infinity, the delta n becomes a circle. You know, so it starts acquiring all possible rotations, all possible reflections.
Yes, sir.
So,
So I
yeah,
had one doubt.
Yeah.
In the D2N group, we represent only rotations and reflections, right? So mathematically speaking, translations are can be represented by the identity element, right? Because
there is no translation for symmetry of delta n.
Okay. So
right?
polygon. So
if I have this plane, this is, let's say, x-axis and y-axis, and I take one square and put it here, I cannot translate this square to get a symmetry. If I translate it any side, it won't go to itself.
Okay, that's because we consider the position of the vertices also.
Yeah. So
Fixed,
because
okay.
So the translation will make sense when we're infinite tile, right? So the tiling of whole plane, you can translate it, then it goes to itself.
Okay.
Right?
Yes.
If you're a single piece, then it then makes sense to translate it. Then it won't go to itself.
Yes, sir.
So there are no translation here.
Yeah, same doubt. Thank you.
Yeah. Okay. So now let's prove that there are only 2n element. So although I have not computed what isometry of R2 is supposed to be, we'll prove this in next lecture. That is supposed to be R2 semi-direct product O2. Don't worry about what semi-direct product is. So this R2 is supposed to refer to translations. So you can translate along the x-axis and y-axis. That's why R2. And orthogonal group is O2, which I just defined. So basically, whatever the isometric group of R2 is, it is composition of translations and the elements from O2. Okay, this will prove, in fact, in the next lecture. So let's assume this, that we have proved this. Suppose I know this. This is R2 semi-direct product O2. Then we are trying to compute that D2n is exactly the symmetric group. So let's call symmetric group is delta n is to be G. We already know that D2n is contained in G, and we want to prove that this is equal. And the way to prove this is equal is that we'll prove the size of G is just 2n. And that's why equality, right? So we know that translations do not keep delta n to itself. So this, whatever the G is, this is supposed to be a subgroup of iso R2, right? G is contained in isometries of R2 by definition. So which is supposed to be this here now. But since there are no translation involved, G is supposed to be contained in O2 only then, right? This simplifies my problem that I have G contained in O2. Now we know that orthogonal group O2 acts on delta n. So how does this act? So I will think of my my object kept centered at origin, right? Like this, that this is the center. I mean, this is a very bad picture of what I mean, but you understand what I mean. That I hexagon, I'll put it at the center. Center of gravity is at the origin. Okay, and this is how. And then I'll number the vertices of this 1, 2, 3, 4, 5, 6. I'll number the vertices. Okay, let's do that. So now if I look at the orthogonal group will act on this because it acts on the circle. It acts on the whole plane, right? After all, it is supposed to be a map from R2 to R2. So it will act on whole plane, and hence it acts on this object also. Clear? This is how I visualize that D2n is contained in G, which is symmetry of delta n. Now, whatever G is, it acts transitively on the vertices. Why does it act transitively on the vertices? That if I look at the action of G on the vertices, there is a single orbit. Why? I'm trying to use group action. I'm going to use that. I told you in the beginning that I will use that.
Because we can, from one vertex, we can reach to any other vertex using rotation.
Yeah, simply by rotation. I mean, you don't have to involve in all elements, right? I can apply rotation. Suppose I want to go from 1 to 3, then I'll rotate by 2 pi by 6 into 2, right? So I will go here. So G acts transitively on the vertex at delta n. So that means there is a single orbit. Now apply the orbit stabilizer theorem. That will say that size of the vertex set xn on which the group is acting is going to be size of G by central stabilizer of one of the point. Let's say one of the vertex is V. You can take V equal to 1, for example, here. So let's call this vertex to be V. Is this clear? I am applying the orbit stabilizer theorem. So I know size of xn is n. I have to compute GV. That will give me the size of G. So let's compute GV. My claim is that GV is of size 2. Of course, there is always identity. And if I try to fix, so what is GV? GV is all those elements of O2 which fix one of the vertex which I have V. So if I want to fix this vertex, that means I am fixing the line passing through origin and that vertex. That means I have to fix x-axis. But as soon as any line is fixed, an element of O2 is supposed to be just reflection along the line. It cannot be rotation. So look at the definition of O2. So it cannot be coming from SO2. It has to be coming from this, the second coset. And there is only one such element which will do that, which will be reflection. Which will be reflection 2 going to 6, 3 going to 5. Okay. So that means GV is of size 2. And that way I can compute the size of G, which will be size of xn into size of GV, which is twice of n. And that is why G equal to D2n. I hope you get the proof here. Any question? It's a simple application of orbit stabilizer theorem.
So just a clarification. So the
Yes.
final part is we know that G is a subset of D2n is a subset of G, and
Yeah.
both sizes are same. That's why they are equal.
Yes, yes. So I know already 2n elements. I mean, I'm using that in fact. That I know that there are certain number of elements which already do that job. Because I used it when I said that it is transitive. I use the known elements to show that it
Yeah.
is transitive.
Correct. Okay, sir.
Yeah. Okay, good. So you see some group theory being used to compute even the simple things here. There are more general version of this idea, whatever I said here. You can ask more complicated question, that wallpaper. So what is wallpaper? That it is not, when you're trying to tile the plane, for example, I mean, it is something similar to tiling, but here what happens that you can have some nice picture here also, right? For example, if I put an arrow in this picture, right? then that also says that I have to adjust it in such a way that this can be done. So sometimes the arrows could be in such a way, or some picture can be in such a way that it can break the symmetry, what is called symmetry breaking. So there are more possibilities. Although the fundamental units will be only 3, 4, 6, like triangle or square or hexagon, but inside that the picture can give you more symmetry, right? And then how many possibility for those things are there, and you can study all that. It's not very difficult. And it turns out that there are only 17 wallpaper groups if you try to classify by their isometries. Okay, this again, you are trying to fill the whole plane, and you can have this n-gun which can have some shading, or which can have some picture or something like that. And so wallpaper group, because you are again trying to fill the infinite plane, it will have two independent translations, and it has the associated finite point group, and it is supposed to be a subgroup of isometric group of R2 again. Unlike DN case, D2N case, where I had a single n-gun. So then there were no translation involved. So it turned out to be a finite subgroup of of O2, or isometries of R2, which is an infinite group. So that there it turned out to be finite group, but these group will turn out to be infinite group always, because there is always a translation along x-axis and, for example, along y-axis or some other axis it could be, because if it is a triangle, then it may not be y-axis. So you can prove more generally that there are 17 possible wallpaper group. And if you're interested in this topic, you can see, for example, the book by Armstrong, titled Groups and Symmetry. It has 2-3 chapters on this, chapter 25 and 26, which will talk about these things in detail. And yeah, it's a good topic to study, like self-study, maybe in summer or some other time. Okay, let me just talk a little bit about what are the regular three-dimensional objects. So this is again, I mean, kind of you might have seen it in high school or some other places. These are called platonic solids. There are three-dimensional regular convex objects which are made of n-guns, and these are called platonic solids. And there are exactly 5 platonic solids: tetrahedron, cube, octahedron, dodecahedron, and icosahedron. I gave a lecture in Science Activity Center, which is a video recorded. It's available on YouTube. You can see that if you want. I don't know whether I should repeat that here, but you can just watch that. I gave some demos using these things which I'm showing you. You can actually construct these objects by having these units. This plastic thing what I have, the hinges here, so you can actually join the hinges and construct these objects. This year, I mean, I also have, just to show you these objects, I also have this Rubik cube. So you can see this is how the cube will be, or this is one of them. What is this called?
Pyraminx, I think. Pyraminx.
Yeah, and then I have this. I mean, I'm just asking in the platonic solids. Don't think of the pictures or anything. So there are only 5 platonic solids: tetrahedron, cube, octahedron, dodecahedron, and icosahedron. And again, this can be proved mathematically. Again, you can use the trick which I told you in the beginning. Using high school math, this can be again proved. So this time, you want to fold it to make a convex object. It is not supposed to be something which is going to fill the plane. So the angle sum is going to be less than 2 pi. Okay. You want less than 2 pi angle sum. So this will give an equation which is like 1 by m plus 1 by m is greater than half. And again, n and m are supposed to be greater than equal to 3. And if you solve these equations, you will get 5 solutions. And these 5 solutions are give exactly these 5 objects which you have here. Okay. It is, if you want, you should watch this video where, I mean, okay, I have also used part of it is in Hindi and English, but it is worth watching if you're not seen constructing from these basic units and how they look like. You can watch that video. But the question is that, can we compute the symmetries of these objects? Okay, so we will do this next time when we define what the symmetry means and what isometry means, and mathematically write it down what isometries are, and then we try to determine what the isometries are. So today maybe we'll stop here. If any question, you can ask me. and we'll get to this next time. The next time we'll do the classification of isometries of an Euclidean space. This will be purely mathematical, and then we get back to the application again later.
So,
Yes.
so somehow, if you take large